Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper machine learning. In this module on machine learning, we are talking about the first module on a specific probabilistic based learning, which is naive Bayes classification, the simplest of the Bayesian learning approach. Before we do that, we will talk a little bit about classification in general before we go to naive Bayes classification. So this is the development team responsible for the creation of this module. Now let us look at the learning objectives of this module. So the learning objectives is to first understand probabilistic classification. We have looked at classification in general before, but here we are looking at probabilistic classification specifically. Then we are going to look at naive Bayes classifier, an important, very important classifier which is simple, makes many simplifying assumptions, but is very practically usable. So that is naive Bayes classifier, and we are going to look at two different application of naive Bayes classifier. So with that, these are some of the keywords: classification, naive Bayes, and independence assumptions that has to do with naive Bayes. Now let us first look at the classification problem per se. So in a classification problem, you will have examples of the form. Remember, classification is a supervised learning, so you have tagged example. You will have D and H of D, hypothesis about D. If it is classified, it will be a class. So where D are the data objects to classify the inputs, and H of D are the correct class information for D. So H of D belongs to 1 to K, where K is the number of classes. So here what we are having is, we are having data, training data of the form, data, and a tag or H of D, which is the correct class into which you want D to fall. So that is the supervised learning approach, the training data. Now the goal is, given a new data, new D, you have to provide the hypothesis or the class of the new data. This is our goal. This is the definition of a classification problem in general. Okay. Now there are many methods in which you can create classifiers. There are 3 methods to establish a classifier. So the first method is model a classification rule directly. These examples are not probabilistic: KNN, decision trees, perceptron, SVM. These are examples of modeling the classification rule directly. Model the probability of class memberships given the input data. So this is an example of the use of probability. So where we try to model the probability of the class memberships given the input data. So you are given the data. Remember, the training data contains the data as well as the hypothesis or the class. Let us simplify it and say class. So data and class. So you are given the data and the class. You are trying to model the probability of the class membership. So example is perceptron with the cross entropy cost. Make a probabilistic model of data within each class. Example of naive Bayes and model based classifiers. So here A and B are examples of discriminative classification, that is, you are trying to discriminate between the classes. C is an example of a generative classification, that is, you are trying to model the data within each class, and B and C are both examples of probabilistic classification where you use probability. So this is methods to create classifiers. Now let us look at probabilistic classification, that is the B and C samples. So we are trying to establish a model or a probabilistic model for classification. In this you have 2 types of models: discriminative model. What is a discriminative probabilistic classifier? So what you have here is x1, x2 to xn, we have the data, and you have the probability of C1, given x the probability of C1, given x the probability of C2, given x the probability of Ck, or how many ever you have the number of classes. And so the probability of C given x is the probability of given C is equal to C1 to Cl, here we are saying L classes, and x is equal to x1 to xn. So this is the idea. So example could be C1 is benign mode and C2 is cancer. So given the data, what is the probability of it belonging to a class? This is called as discriminative model, where you model the class. Okay. So the next model that we have is generative model. Here we have the data, and given us data, you have the probability that this fruit is an apple, for example. Then again, given the data, the probability that this fruit is a something else, and some other class, and probability that this fruit is an orange for example, and you are given a vectors of random variables. This probability that this fruit, so you are trying to generate a model for each class. There you are given the data, you are trying to find which is the model that fits the data or class that fits the data. Here we are trying to model each and every class separately. So, that is called the generator model. Now, with this fundamental about general classifier, probabilistic classifier, discriminative and generative probabilistic classifier, let us go into the simplest of classifier called the naive Bayes classifier. So, before we go to that, let us describe Bayes classification in general. So, given a data X, we want to find the probability of the class C is normally found or directly proportional to the prior probability of the class C and the likelihood of the likelihood, that is given the class C, what is the probability of the data, and this is written as, if you have so many data points x1 to xn. So, given the class C and the probability of find the probability of x1 to xn and the probability of class C. Now, the problem is that actually for you to find the likelihood, you need to find the joint probability of x1 to xn, that is given the class C, what is the probability of all the data points fitting into this class C jointly. That is what actually is Bayesian classification. However, there is a difficulty in learning this joint probability classification. It is a very expensive issue. Therefore, they came up with something called as naive Bayes classification. So, in order to avoid the joint probability, we assume in the joint probability we assume that all the data points contribute jointly to the classification, which is actually true. But we are making an assumption, we are making an assumption that all the input attributes, that that data point is associated with are conditionally independent. Again I will tell you, we are taking all the data points corresponding to a vector, and we are assuming that all jointly only those attributes will contribute to the classification, but we are assuming that all the input attributes are conditionally independent. Therefore, P of x1, x2 to xn given C, what is the probability of x1, x2 to xn, is now divided as given x1, x2, xk to C, what is the probability of x1 given x2 to xn C, what is the probability of x2 to x1 given C. This is again reworded, and finally you get probability of the first attribute given C, probability of the second attribute given C, probability of the third attribute given C independently. So, now you have reduced this to a product of individual probabilities of each attribute given C rather than the joint probability of all attributes given C, and this is the very important conditionally independent assumption that we make for naive Bayes. Okay. So, let us again re-emphasize this. So, the naive Bayes classifier, the important special simplification of a Bayes optimal classifier. Optimal classifier is one which takes the joint probability. The simplification of that is all attributes are independent given the class. So, attribute 1 is independent, attribute 2 all are independent. So, along with decision trees, neural networks, nearest neighbor, one of the most practical learning methods. So, when to use it? You moderate or a large training set available. Attributes that describe instances are conditionally independent. So, when do you use naive Bayes? When there is moderately or large training set available, and attributes that describe the instances are conditionally independent given the classification. This is not always true, but at least somewhat independent. Successful applications include diagnosis and classification of text documents, very largely used for this. And one practical Bayesian learning method, as we said, practical because it is simple to apply, applies to learning tasks where each instance x is described by a conjunction of attribute values and where the target function f of x can take any value from the finite set V. So, input a set of training samples is provided, a new instance is described by a tuple of attribute values a1, a2 to an, and the learner is asked to predict the target value, which is a classification for this new instance. This is the scenario. Now, the assumptions are P of Cj, that is can be estimated from the frequency of classes. That is, what is P of Cj? That is the prior probability of a class. We are assuming this prior probability can be estimated from the frequency of classes in the training data. So, if you give the training data properly only, you will get the naive Bayes also properly, and we can if you want to actually determine the joint probability given like this x1 to xn is given the class, it could be estimated only if a very large number of training examples are available. That is why we go for the conditional independence. Not only the costly nature of finding the joint probability, it is impossible to find the joint probability, any probability in that joint probability with small number of samples. It has to be huge number of training examples, because this joint probability should be available, right. So, we go for conditional independence assumption again. So, we are telling a second point why we should go for conditional assumption. Assume that the probability of observing the conjunction of attribute is equal to the product of the individual probabilities. Now, so let us define the naive Bayes classifier. Let each instance x of a training set D be a conjunction of n attribute values a1, a2 to an, and let f of x the target function be such that it belongs to a finite set. So, again we are defining the Bayes approach, the maximum a priori. So, what do we do here? We assume that this is the normal maximum a priori, where we have that the classification which is giving you the maximum probability of the likelihood, which is the joint probability of the attributes given the class, and the prior probability of the class will be the class that is the probable. But naive Bayesian approach, we assume that the attribute values are conditionally independent and therefore not too large a data is necessary. So, we replace the maximum a priori by V n of naive Bayes is equal to argument max. We find a Vj belonging to V. Vj is the target function, which is probability of Vj, that is the prior probability, and the product of all the probability of Vj given each of the attributes. So, suppose you have n number of attributes, the product of all the individual properties of the n attributes. So, that is the modified definition or of the naive Bayes definition. So, the naive Bayes classification, the naive assumption is attribute independent. So, the joint probability is replaced by the product of the probabilities. Now, if the ith attribute is categorical, then P of xi, that is the likelihood, that is the probability of xi given C, is estimated as the relative frequency of samples having xi as ith attribute in the class C, okay, the value. If ith attribute is continuous, then P of xi is estimated through a Gaussian density function, which we discussed when we discussed about general discrete and continuous cases. So, computationally easy to determine this likelihood for each attribute independently. It is quite easy to do this. Now, the naive Bayes algorithm for discrete input attributes has two phases, both has two phases. One is a learning phase and one is a test phase. So, the learning phase is used for finding out the likelihood in the prior, and the test phase is used to find the actual classification. So, for each target value, so for each class you estimate the probability of the prior probability of that class in the sample set. Then for every attribute value that you have, for each attribute up to n and each of the classes, you try to find the likelihood for probability of that particular attribute for class 1, probability of that particular attribute for class 2, and so on up to all the classes, k classes, and the probability of each and every attribute for each and every class. So, this is first done with for all the examples of SI. Let us assume that we have 5 classes and let us say 100 attributes. Okay, each attribute, we are not talking about examples, attributes. Suppose we say we have 10 attributes and 5 classes, then we have to find the probability of all the 10 attributes for first class, all the 10 attributes likelihood for the second class, like that each and every one. So, we will have altogether for class 1 we will have 10 probabilities, for class 2 we will have 10 probabilities, and so on. So, that is the training phase or learning phase. In the test phase, given an unknown instance of attribute values, you have to look up the table and assign the probabilities appropriately, and then you have to find out which product gives you the maximum probability, that particular class, which class of combination gives you the maximum. So, it will be prior probability of class 1, let us assume, into the probability of the likelihood of the attribute for that particular class. You calculate the probability product, do that for every class, whichever gives you a maximum, that will be your class for the new variable. So, this is the naive Bayes algorithm. So, assume target function, and this is the map. So, we are doing it like this. Here we have just written it in the form the normal maxima a priori where the joint probability is considered. Here we are just taking that we do not consider the evidence, because evidence, to find a maximum you do not need to find the evidence. And for naive Bayes algorithm, for each target value you estimate, and here we replace it by the product. We have already seen this. So, NB is the argument max, only difference is instead of taking a joint probability of all the attributes, we are taking the product of each attribute for each value. Okay. So, this is the assumption and this is the product that we get. Now, characteristic of naive Bayes only requires the estimation of prior probabilities P of C of k and P conditional probabilities for each class, able to answer full set of queries across classes and across features. So, empirical evidence shows that naive Bayes classifiers work surprisingly and remarkably well. The use of full Bayes belief network provide only limited improvements in classification performance. That was what has been found. Now, let us take an example. The example we are taking here is playing tennis. So, this is a famous example that is often used to discuss naive Bayes. So, as you can see, we have 14 days and we have 14 samples, and we have 4 attributes, outlook, temperature, humidity and wind, and this is often used for other machine learning algorithms also. Then we have played tennis. So, that is the classification you want, whether tennis was played or not played. Okay. Now, how do you calculate prior probability? You just count the number of S's and number of no's. So, you will see that there are 1, 2, 3, 4, 5 no's out of 14 samples. So, 5 by 14, 9 by 14 is for yes. So, that is the first one, prior probability of the class. So, here we have only Boolean class yes and no. Now, we have to do the next step, we will see. Given this training set, we compute the probabilities. So, here we have sunny. So, out of the total 9, how many sunny, when it was sunny, outlook was sunny, how many did you get? So, we will just go back. So, like that you can find out. So, let us look at sunny alone. So, if you look at sunny, 1, 2, 3, you have 3 sunnies and no, out of 4 no's, 3 sunnies gave a no, and out of that rest. So, that is the way you calculate. So, out of the 5, 3 gave no. So, like that you can calculate for each of the attributes. So, actually what we are doing here is, now outlook has 3 values, attribute outlook has 3 values for each of the attributes, positive, negative. Positive total is 9, negative total is 5. So, we are trying how many, when it was sunny, how many gave no out of the 9, how many gave like that. I mean, how out of 9, how many were given sunny, sunny value was there, like that for overcast, like that for rain. Similarly, temperature had 3 attribute values for that. Similarly, humidity and windy and humidity were Boolean. So, this gave you the likelihood probabilities or conditional probabilities as they are called. Now, given that outlook, we have already calculated this, and we have got these values. So, for humidity, for windy, for temperature, for outlook, and we have got the prior probability. So, this is the estimation which we saw in the last slide also. So, now that is the training phase, calculating the tables. Now, the test phase is given a new instance. What are we given? We are given that the outlook is sunny, the temperature is cool, the humidity is high and the wind is strong. Now, given these 4 values of the 4 attributes, now you try to find out what is the probability of yes given this x dash. Now, for that you have to find the probability of sunny yes, cool yes, high yes, those are the values there, and strong yes, and multiply it by the probability of yes, play yes. So, you get the probability of 0.0053. And if you do the same thing for no, you find out that there are only 2 classes, you find 0.02, 0.06. So, we have actually done a map rule here to calculate yes and no. So, you have taken the independent likelihood probabilities into the prior probability, and we got 0.053 for the class yes and 0.2, 0.6 for the class no. So, given this fact, we label x dash as no, because that gave you the maximum probability. That is what is called as maximum a priori posterior probability. Now, let us take another problem, which is a very famous problem, the defining of text classification. So, what we do here is we document D is a multi-dimensional space X, and we have classes or labels. Let us assume we have J labels and the training set of label documents. So, documents are given and the class is given, and we want to find out the target function given another document X, what is its class. So, this is a learning algorithm is needed. So, for example, Beijing joins the World Trade Organization, comma China. So, that is the class. So, the class here is China and the document has class C. Now, there are many uses of text classification. Text classification is the task of classifying text documents into multiple. So, is the mail spam? Is this article about computer or music, miscellaneous piano? Is this article likely to be relevant to user X? Is this page likely to lead me to pages relevant to my topic specific crawling? There are a lot of applications, especially in today's world, social network applications, web search applications, product applications, online shopping applications, lots and lots of applications of text classification are coming up. Now, so as you saw, text classification is an important problem. So, let us learn to classify text. So, learn from examples which articles are of interest. What are the attributes here? The attributes here are the words in the documents. Now, the naive Bayes assumption makes sure that we have a random sequential model within each class. Naive Bayes classifiers are one of the most effective for this type of task. So, text, given a text document X, n is the number of word occurrences in X, return the category. Now, what we are trying to do here is probability of Ci, what is the class prior probability, probability of the attributes given the class, where ai is the word occurring in the ith position in X. Now, we will come back to this. Here we assume that we are talking about a position. Okay. Now, the text naive Bayes algorithm training, let V be the vocabulary of all the words in the document, and for each category Ci belonging to C, let Di be the subset of documents in that particular category. So, probability of Ci is the number of documents belonging to that category divided by the total number of documents, and let Ti be the concatenation of all the documents in Di, and let the total number of words in that all those documents be Ti. So, for each word, let Nij be the number of occurrences of that particular word in Ti. So, now we are defining the likelihood. So, Cj given the class, the probability of Wj is equal to Nj plus 1 divided by what is Nij? Nij is the number of occurrences of that particular word in Ti, Nij plus 1, I will tell you why we are using plus 1 again, divided by the total number of word occurrences plus the vocabulary. So, this is how it is done for text training. So, this is a slightly different definition of exactly what is conditional probability here. So, the common practice is maximum likelihood, simply we use the frequency. So, similar thing we have done here. So, the probability of prior probability of a class is the total number of instances of that class, number of instances of belonging to that class divided by the total number of instances, and likelihood is probability of that word coming in that class by the total number of words in the number of categories. So, the problem with the maximum likelihood is there is some problem here. If there are no training cases of patient has no flow and muscle aches, what will happen? You will get a probability of 0. So, if you get a probability of 0, that is prior probability is 0, then what will happen? Cannot be conditioned away no matter what the other evidences, you will still get a 0 probability, which is not true, because it is the probability is 0 because you have not come across that. So, attributes are text positions, values are words. So, that can be done, but still there are too many possibilities. Assume that classification independent of the positions. So, then you come across what is the famously called the bag of words model. So, there we just take words, the occurrence of the words is enough, we are not bothered about the positions of the words, and you calculate the probability. So, let us take the example here. You have 4 documents, it is a very small set, it is a toy set, just to show you the example. We have seen a little bit of an example, this is to make you understand it more in detail previously, much before when we were talking about probability. So, here you have 4 documents, and all of them, 3 of them are classified. You want to know whether the document class is China or not China. So, you have out of the 4 training documents, 3 are China and 1 is not China. So, the prior probability of yes and not China and not China is 3 by 4 and 1 by 4. This is straightforward. Then next is we have to calculate the see if the word Chinese occurs, what is the probability of it becoming the class being China. So, here we are using the previous model. So, Chinese comes in 1, 2, 3, 4, 5, it comes 6 times total number, and the total number of words is how many, and 5 plus 1, that is it comes 1, 2, 3, 4, 5. In S it comes 5 times, you add 1 to that, so you get a 6 divided by 8, the total number of words in S 1, 2, 3, yeah 8, out of which plus how many times Chinese comes 1, 2, 3, 4, 5, 6. So, the vocabulary, so Chinese, Beijing, Shanghai, Macau, Tokyo, Japan. So, 6 words. So, 8 is the total number of words in the S documents and 6 is the vocabulary. So, you get 3 by 7. Similarly, you can take Tokyo and C, and equal to Japan C is equal to 0 plus 1, 8 plus 6 is the same, 1 by 14, and P of Chinese not China is equal to 2 by 9, and the similar thing you get. So, with this, for the new document given Chinese, Tokyo, Japan, you get P of C given the D5 is equal to 3 by 4 into 3 by 7 the whole cubed, okay, into 1 by 4 into 1 by 4, that is equal to. Why the whole cube? Because of the words. So, you can we have done the calculation before, and you find that it is for C, that is Chinese, you get a probability of not 3, and for not Chinese you get not 1. So, this is the example. So, why does the naive Bayes classifier work? It is easy to implement, it is good learning speed, classification speed, modest storage, supports incrementally, recommendations can be written as attribute values of the new items become known. It seems to work well in very many scenarios. But why does it work well? It has wider ranges of applicability than previously thought in spite of the independence assumption. Classification accuracy is different from probability estimate accuracy, that you must remember. Probability estimate it gives correctly, but what about the classification accuracy? So, advantages easy to implement, good results most cases. Disadvantages, of course, the assumption of class independence, conditional independence, therefore, loss of accuracy. Practically dependencies exist among variables, you cannot assume that they are independent. For example, hospitals, patients, profile, age, family history, all these are connected. Symptoms, fever, cough, those are connected. Disease, lung cancer, diabetes is connected. So, the dependency among these variables cannot be modeled using naive Bayes. The model does not allow that. So, how to deal with these dependencies? That is the Bayes belief network, which we will discuss later. Now, the issues relevant to naive Bayes, the violation of the independence assumption. For many real world tasks, events are correlated, nevertheless naive Bayes works. The other problem is the zero conditional probability problem. Such problem exists when no example contains that particular attribute value. So, this is a problem because you will get a 0 value and that particular result will be wrong. So, what you do? You put conditional probabilities with virtual examples. So, we have estimated probabilities by the fraction of times the event is occurred to NC occur over the total number. It provides poor estimates when NC is very small. If none of the training instances with target value Vj have attribute AI, what happens? You will get that equal to 0. So, for that what you do is when NC is small, N is the number of training samples, NC is the number of samples which for which this is a V equal to Vj and A is equal to AI, P is the prior estimate, M is a weight given to the prior number of virtual samples. So, in this way what you have done is you have modified the calculation of the probability such that you do not get a 0 value for the conditional probability, you get a small value. So, what we have done here is we have explained the concept of probabilistic classification, we have explained the naive Bayes classifier in detail, one of the first probabilistic learning algorithms or methods we have seen, and we have discussed some applications. We took 2 applications, one was a typical application of machine learning, the playing tennis problem, and then we took a text application problem where we spoke about the 2 conditional probability, how we where we had little bit of dependence then remove the dependence, and then the second one was the 0 conditional probability assumption. So, this is what we discussed here. Thank you.